Hello everyone, thank you for joining us today at PIMRC 2021. My name is Tuong. Today I'm going to present our accepted paper, Traffic Prediction for Reconfigurable Access Scheme in Correlated Traffic Machine Type Communication Networks. The presentation is organized as follows. First, I will briefly introduce the motivation behind our work. Then I will present the system model and the time frame structure. Then I will talk about the traffic model adopted in this work. Then I will present the learning-based access scheme for correlated traffic machine type communication networks. In this section, I'm gonna present the problem description and the algorithm. Then I will show the illustrative results, and finally I will conclude the presentation. In 5G and beyond network, the focus will no longer be human type communication. Instead, we will focus on machine type communication networks. However, machine type communication has unique characteristics. First, it has large number of devices. Second, devices usually report events, so they are likely to have a correlated traffic. In this study, we consider machine type communication networks with correlated traffic. So, in the adopted traffic model, devices that are closer to events have higher probability of being triggered into alarm mode with high packet arrival rates. In other words, devices have spatially correlated traffic. For system model, we consider a multi-point-to-point machine type communication network having D devices. The base station is massive MIMO with M antennas, and devices are single antenna. The time frame, as shown here, is divided into two segments. First, we have a CRAN-based segment where devices are reserved time slots and preambles, so they can transmit without collisions. And we also have here a CRAN-free segment where devices have to contend for transmission by P persistent or aloha as follows. With probability P, a device having data packets randomly chooses a preamble and transmits the preamble followed by its data. If the selected preamble is also selected by any other devices, preamble collision happens and the transmission is failed. So the question arises, how can we schedule devices in the CRAN-based segment, and how can we calculate the access probability of devices in the CRAN-free segment? To do this, we use algorithm 1 in this work. Basically, this is our previous work where we propose an iterative algorithm. And the algorithm works as follows. First, we set the length of the CRAN-based segment NGB to be 0. Then we repeat the iterative algorithm. In each iteration, we increase NGB by 1. Then we allocate devices having high non-empty queue probabilities to the CRAN-based segment. And then we calculate P for the rest of devices. And we notice that in this algorithm we need the non-empty queue probabilities. For traffic model here we presented a figure to illustrate our traffic model. In this traffic model, when the event happens here, device 1 and device 2 will have higher probabilities of being triggered to the alarm mode than device 3 and device 4 because they're closer to the event then device 3 and device 4. We model the traffic model as a two-state Markov chain with the regular state having low packet arrival rate and the alarm mode has high packet arrival rate, and the probability of being triggered into the alarm mode PXD is larger when the device is closer to the event. So as I mentioned before, the base station needs the probability of having a data packet of each device D. This probability can be easily calculated if we know the traffic model parameters and the event's position. However, in reality, the event's positions are not available and the traffic model is too complicated to learn. And in addition, events can happen at any places and we cannot predict the events. So instead, the base station has to exploit the spatial correlation to predict the non-empty queue probability in the current time frame. So mathematically, we have to predict the probability of having non-empty queue given the set of devices transmitting that data in the previous time frame. In the proposed algorithm, during the first NF time frames, devices have to record the queue states, and after NF time frames, devices transmit their records to the base station, and the base station constructs a traffic dataset queue from the device records. Here we show an example of the dataset with 4 devices and 4 time frames. Here, this value here is 1. It means that the device has a data packet. Device 4 has a data packet at time frame 3. We propose a scalable learning-based algorithm to predict the probability of having data packets. The algorithm has 2 steps. In the first steps, we cluster devices in different ways, and for each cluster we train a neural network taking the traffic data of the previous time frame and predict the traffic data of the current time frame. And here we have an illustration of the learning procedure. And when we make the prediction, we average the prediction of the device, and we interpret the prediction, the average prediction, as the probability of having data packet. And here is the illustrative results. Here we consider the proposed access scheme with other 3 schemes. The first one is a no statistics scenario where the base station knows the event position and the traffic model parameters. So this is an upper bound representing the best case scenario. We also compare the proposed access schemes with other 2 baselines. The first one is a random scheduling where we fixed the length of the grant-based segment to NGB max, which is the maximum allowable length of it, and we randomly select devices for this segment, and we set the probability of transmission in the grant-free segment to 0.2 for all devices. Then we have another baseline called optimized random access, where we don't have the grant-based segment, and we optimize the access probability. As we can see here in this figure, the proposed learning-based access scheme has higher throughput than the random scheduling and the optimized random access. And in addition, we can see that when the number of antennas at the base station is low, there's a large gap between the proposed scheme and the known statistic. However, when the number of antennas is larger, the gap tends to narrow down. And this is because when n is larger, more devices can, the interference cancellation is good, so more devices can transmit. So the base station has more information to make prediction. In this figure, we plot throughput versus the number of preambles at the base station, and our proposed scheme is also better than the optimized random access and the random scheduling, and also it is close to the known statistic scenario. In this figure, we plot throughput versus the signal-to-noise ratio, S and R. As can be seen from this figure, when the S and R is low, all the access schemes achieve low throughput. Well, this is understandable because when the S and R is low, we have the domination of noise. However, when the S and R is larger, we can see that our proposed scheme achieves higher throughput than the other two baselines, and it also has close throughput to the node statistic. So in conclusion, in this presentation, we propose a learning-based access scheme for machine-type communication networks with massive MIMO base station and devices have spatially correlated traffic. The base station is not provided with the traffic parameters of devices, so it has to exploit the correlation in device traffic to predict the probability of having data packets of devices. And the estimated probabilities are used to schedule devices and reconfigure the transmission parameters. We also carry out simulations to verify the effectiveness of the proposed access scheme in terms of throughput. And we see that the proposed access scheme achieves higher throughput than random scheduling and optimized random access. Well, that's the end of the presentation. Thank you for listening.